All right, our next example, we're going to put it all together. We're going to find the zeros and their multiplicities of f of x equals 1/2 quantity x plus 1 times 2x minus 3 quantity squared. So fortunately, this one's going to be a little bit easier for us to find the zeros because of the fact that it's already factored for us. We don't have to do any factoring. They've already put it in the right form for us. So all we have to do is set our function equal to 0. And then set each one of the factors equal to 0 and solve. Now the 1/2 out in the front doesn't have to be set equal to 0 because there's no x's involved, so I don't have to worry about that one. I do have to set the x plus 1 equal to 0, and I have to set the 2x minus 3 equal to 0 and solve both of those. In the first one, x plus 1, we'll subtract 1 on both sides. We get x equals negative 1. In the second one, we have to add 3, and then we'll divide by 2, so x will be 3/2. Now in the first one, the exponent on the parentheses, well, there is no exponent written there, and we don't typically write it, but the exponent on that parentheses is a 1. You just don't typically write that. And because that's an odd number, it's an odd exponent, this has a multiplicity of 1, which means it's going to go through the graph. Now the second one had a multiplicity of 2 because of the fact that there's a squared on it. That has a multiplicity of 2, which means that this one is going to bounce or just touch the graph at 3/2 and then go the opposite direction. So let's go ahead and take a look at, since we have our zeros, let's go ahead and take a look now at the end behavior. So the power on this thing, the degree. Now remember, the first one, there's nothing to do with the half. That has nothing to do with it. The first parentheses is a 1. The second parentheses is a squared. Now really, the easiest way to figure out your degree is to simply add up the multiplicities. Once you add up the multiplicities, you have your degree. So in this case, the multiplicities add up to 3. That is the degree. Now I do have to look at the leading coefficient. Now the leading coefficient, again, be very careful on this one. The leading coefficient of this piece right here is a 1. The leading coefficient on that one right there looks like it's 2, but the 2 is technically squared because of that, so it's really a 4. And this 1/2, this is where the 1/2 actually comes into play, would have to actually be, whoops, sorry about that. The 1/2 would actually have to be taken into account as well for the leading coefficient. So really it's going to be 4 times 1 times a half. 4 coming from this one, 1 coming from this one, and then the half out here. So the leading coefficient is 4 times 1, which is 4, times a half is 2. Ultimately, I didn't really need to know the number as much as I needed to know that it was positive, because that tells me my end behavior, since the degree was 3, it's odd, which means they go opposite directions. Positive means it's going to start down and finish up. So let's take a look at the sketch of what this would look like real quick. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Doesn't have to be perfect, just trying to get a general idea. So I know my zeros are going to be x equals negative 1. There's one of them. X equals 3/2, which is 1 1/2, so it's going to be about right there. Now the one thing I do know is the end behavior. End behavior has to start down. So from here it's got to go down. And then it's got to finish up. And you might look at that and think, well, how in the heck is that going to happen? Because how am I going to go through the first one and then, well, again, you are going to go through the first one, but you're going to bounce off the second one. So this one is going to actually look something like that. And this one's going to go through something like that. So they're going to connect in such a way that it looks something like that. All right, I know it's a lot of information. Hopefully you're starting to grasp the idea of this. All right, we're going to talk about one last concept in this unit, which is called the intermediate value theorem. and then we're going to do one last example of putting all the graphing stuff together to get a decent idea of what the graph is. So let's talk about this thing. Whoops, sorry about that. Let's talk about this thing which is called the intermediate value theorem. Alright, so intermediate value theorem. Here's the general idea of the intermediate value theorem. If I were to have some kind of a graph, maybe it looks something like this. And I want to find the zero of this thing, or at least figure out that the zero of this thing exists. Maybe by looking at the graph, or maybe by the function itself. I can't really factor it. It's just not going to be an easy function to factor. The idea is, if I can find some kind of a value, maybe here, we'll call that A, and some kind of a value here, B, that I can actually find the value of this graph. So meaning that I can find the Y value here. That's going to give me some kind of a value, a Y value. We're going to call it f of B. That's just a Y value. And then this is going to give me some kind of a value down here. We'll call that f of A. The idea is, if I can find these two values, the intermediate value theorem says that because I know that this is a continuous function of some kind, it's a continuous polynomial, every Y value between here and here has to be taken on someplace in between A and B. In other words, there's no way that I can draw this function right here. There's no way I can draw it without taking on every Y value between here and here. I've just got to. Every Y value has to be taken on there. So that means if I can find a Y value that's less than 0, like f of A, and a Y value that is greater than 0, like f of B, then I know that because the function has to go from some negative number to some positive number, it's got to cross through the x-axis somewhere. I may not be able to find that value easily, but I do know that it has to exist someplace. Very, very complicated to actually put into words, much, much easier to do. So let's actually take a look at an example of this thing, and I will show you how easy it actually is to figure this out. Here is our example. Let's say that I have f of x is x cubed minus 2x minus 5. All we're being asked to do is we're being asked to show that this function right here has some kind of a zero or a root or a solution someplace on that graph. In between, let's say, in between 2 and 3. So if we were to graph it, we would actually be able to see it. Just someplace in between 2 and 3, we're going to be asked to show whether this thing has a zero or a root. So the problem is this thing does not factor easily. It's x cubed minus 2x minus 5. Even if it was x squared, it would not factor easily for us. But all we're being asked to do is show that it actually has a zero someplace. Well, here's the thing. Here's all you have to do. I'm going to take the function and I'm going to evaluate it at 2. If I plug 2 in there, we're going to get 2 cubed minus 2 times 2 minus 5, which is going to be 8 minus 4 minus 5. 8 minus 4 is 4. Minus 5 more is negative 1. So that's a negative value when I plug 2 in. Now if I plug in 3, I'm hoping this is positive. So I'm going to get 3 cubed minus 2 times 3 minus 5. 3 cubed is 27. 2 times 3 is 6, minus 5. So 27 minus 6 is 21, minus 5 more is 16. So what you can see is that I have a negative value here and a positive value here, which means the only way that I can go from -1 to positive 16 is if I pass through 0 at some point on my graph. So by the intermediate value theorem, which I'm not going to keep writing out, shows there is at least one 0 between the x values of 2 and 3. Didn't ask us to find the 0, just wanted us to show that at least one exists. Okay, and again, that's going to be important for much higher level math, but that's what the intermediate value theorem states. Very easy to do. Hopefully you will not find that difficult to actually show when it comes time for the problems. All right, last example. If you think you've got it all, you probably don't even need to watch this one, but I'm going to do one more example of where we're going to graph a polynomial function. We're going to put it all together. So f of x will be -2 times x minus 1 squared times x plus 2. So again, I want to go ahead and I want to find the zeros. So we'll set the whole thing equal to 0. I don't have to do anything with the -2 yet. That will help us to determine the direction. But it doesn't have any x's attached to it, so it doesn't have to do with the zeros. I do need to take the x minus 1 and set that equal to 0, and I need to take the x plus 2 and set that equal to 0, and I'll need to determine the multiplicities as well. So if I solve the x minus 1 by adding 1 to both sides, that's x equals 1. Now that was inside the x minus 1 squared, so this one has a multiplicity of 2, which means it's going to bounce, touch, but not go through. The second one, subtracting 2 on both sides, we get that x equals -2. That one did not have an exponent written on it, so we assume it to be 1. Well, it is 1. So that has a multiplicity of 1, which means it's going to go through the graph. Okay, we're going to talk about the degree. Remember, the easiest way to find the degree is to add the multiplicities. So we have a multiplicity here of 2 plus 1, or 3. And the leading coefficient, let's see, the leading coefficient here is 1. The leading coefficient here is 1 squared, which is also 1. And then the leading coefficient out there is -2. So 1 times -2 is -2. The degree was 3, so it's odd, going in opposite directions. The fact that the leading coefficient is negative means that it's going to start up and finish down. Remember, negative generally in a down direction. So let's go ahead and look at the graph. And remember, the degree 3 means it can have a maximum number of turns of 2, so it should turn twice in this case. So let's go ahead and put some values on here. Take a look at this, see if we can sketch this thing pretty well. I should have x-intercepts at -2. Whoops, wrong color, sorry. -2 right there, and +1 right there. The ends should go up, so up here, and then down over there. The 1 is going to have a multiplicity of 2, so it's going to bounce off the graph. The -2 has a multiplicity of 1, so it's going to go through the graph. So this one's going to go through here. Then it's going to come up to this one, bounce off of it, and then finish down. All right, so those are the things that you're looking for in the graphs. If you got that general idea, then you should be doing pretty good. That is the end of 3.2.